Hello everybody, and welcome to Theorem 1.5 on page 22. So we are going to close this section by talking about one theorem here. Okay, let's read what this theorem is saying. So it's giving us a vector space V and a subset S of V. And the theorem tells us two things. Number one, that the span of the set S is a subspace of V no matter what the set S is. Okay, this is kind of an interesting result because it's saying that if you take any bag of vectors in your vector space and take the span of it, you're always going to get a subspace, no matter what that bag looks like. Okay, and then the second one says that any subspace of V that contains S also contains the span of S. Okay, what we're going to do here is just prove the first part of this. If you're interested, you can look at the textbook and see the proof of statement number 2 here. All right, so let's see if we can do that. So just to remind you, we'll just be proving part 1. Okay, and our strategy is going to be to break this into two cases. Okay, and the first case is, what if the set S is empty, if it contains no vectors? Okay, we'd like to convince ourselves that the span of that set S, the span of the empty set, is a subspace. Now, this is kind of a strange situation because what does it mean to take the span of a set of no vectors? It's kind of like our bag is empty, so what would it even mean to talk about linear combinations of vectors in S? Well, our book, just by convention, defines the span of the empty set to be the zero vector, and it's just a definition that happens to be convenient. Okay, the zero vector. Okay, and because the textbook defined it that way, and I'll just remark that as we get a little bit farther into the course, you might get some insight into why we would define the span of the empty set this way. For now, it's kind of mysterious why we would want to do that. Okay, but if we take that as our definition, the set that contains just the zero vector actually fits all of the criterion that we need to have a subspace. I'll let you think about that and check that on your own. Okay, this one element set that contains the zero vector is a subspace of V. Okay, that's what we wanted to prove. So in the case where S is the empty set, we're done. Okay, the more interesting case is, what if S is non-empty? Okay, well, if we start with a non-empty bag of vectors, then it's possible to choose a vector in our set. So let's do that. We'll call it X. Okay, and we're going to use our usual tool for showing that something is a subspace. We'll use Theorem 1.3. Okay, what were the criteria that we need to check for Theorem 1.3? Well, seems to me that there were 3 of them, and the first one asked us to demonstrate that 0, the zero vector, is in the thing that we're trying to show as the subspace. So we'd like to show that the zero vector is in the span of S. Okay, well, what does it mean to be in the span of S? It means that we can write the zero vector as a linear combination of the vectors that are in S. Okay, and here's one vector that's sitting in our bag of vectors S. And notice that we can write the zero vector as 0 times that. Okay, and that's a linear combination of the vectors in S. It's a very simple one, 0 times x, but that by definition is in the span of S. Okay, and so we have just verified condition A in Theorem 1.3. The zero vector lives in the span of S. Okay, and then B and C were about closure. We'd like to prove that if we start with any two vectors x and y that are in span of S, that their sum and any scalar multiples of those vectors stay in the span of S. Let's see if we can do that. So we'll start with any vectors x and y in the span of S. Okay, and we'll take any scalar. Okay, C in our field. Okay, and before we get rolling with the proof, it would be helpful to think about what it means for x and y to be in the span of S. Okay, that's kind of our starting assumption here. Okay, and again, that just means that we can write both x and y as a linear combination of vectors in our set. Okay, so we'll start with the x. So since x is in S, that means that there exists scalars, I'll call them a1 through am, and vectors, I'll call them u1 through um in S, such that x looks like a1 u1 plus a2 u2, okay, and so on. Okay, that's just what it means to say that x is in the span. We can build it as a linear combination of some vectors from our bag S. Okay, and we can make a similar statement about y. So let's say it this way. Similarly, y is in the span of S. So there exist some other scalars. We'll call them this time b1 through bn. Okay, and some other vectors, v1 through vn. Okay, so that y is a combination of those vectors, b1, v1 plus b2, v2, all the way up to bn, vn. Okay. And therefore, let's think about where we're going with all of this. We'd like to show closure under addition. Okay, so we'd like to convince ourselves that if we take x plus y, that sum is going to stay in the span of S. Okay, well, what does that sum equal to, first of all? Well, we have a representation for x here and y here. So if we add those together, we're going to get x plus y. This is going to lead us to kind of a long equation. So let me move this to the left just to make sure that we have room for this. So a1 u1 plus up to am um, there's our x, plus b1 v1 all the way up to bn vn. And now take a look at that equation, or take a look at the expression on the right-hand side, and ask yourself kind of what are we looking at? Okay, if you sort of go to every one of these vectors one at a time and underline them, notice that all of those vectors live in the set S. And so we're looking at just a very big, long linear combination of vectors in S. And that, by definition, means that x plus y is in the span of S. Okay, that's what we wanted to show. That shows closure under addition. Okay, what about scalar multiplication? Okay, well, if we take a scalar c and multiply by x, we're going to get c times, let's see, a1 u1 up to am um. Okay, and if we simplify that down, we can rewrite that as c1 a1 u1 plus, or I'm sorry, just ca1 u1. Okay, and we would continue until we get to the last one, which looks like cam um. And notice that that's just a linear combination, again, of the vectors u1 through um. Okay, so that by definition is also in the span of S. Okay, so if you look back at what we showed in this B/C part of our proof, we just showed closure under addition and scalar multiplication. Now we have everything that we need to be able to say that by Theorem 1.3, span of S is indeed a subspace of V.